Welcome to the Cosmic Savannah with Dr. Jacinta Delhaize,
Dr. Siamiso Makwela,
and Dr. Daniel Kanema. Each episode we'll be giving you a behind-the-scenes look at world-class astronomy and astrophysics happening under African skies.
Let us introduce you to the people involved, the technology we use, the exciting work we do, and the fascinating discoveries we make.
Sit back and relax as we take you on a safari through the sky.
Welcome to today's episode.
Hello, everybody.
That was enthusiastic. Hi, everyone.
Tia is on form today, so we're going to let her lead this. Tia?
Well, I'm trying. I'm not really on form. I'm just, trying to be alive in this cold, breezy weather that's not really nice. So I'm just trying to find some positivity around.
We appreciate it.
I love it.
And I have to spread it to both of you.
Yes,
Yeah,
please.
thank
We
you.
need it.
No, I'm full of beans.
It's quite chilly in our little tiny studio at the moment. Winter is very much in Cape Town. Dan's wrapped up in a nice scarf. Is that cashmere, silk? What you got there?
It's from Ethiopia, actually.
Oh, very nice.
Yeah, it's very nice. Thank you. I don't know what it's made out of. Cotton?
Yeah, let me feel the texture.
It feels really good. It feels like a good quality scarf.
When we were there for the Dark Skies and Astrotourism Conference, Astronomical Heritage Conference in November, one of the organisers, Mariana Povic, who we've spoken to previously on here, she took us to this community project with these women who could no longer work in the work that they were doing, which was hard to talk about, collecting wood. Once they became too old to collect wood, they started this little organization where they make scarves and other cloths and things. So we went in and saw this and met them and watched them making these fabrics on traditional looms. I think they're looms.
Oh, really?
Yeah.
Wow.
And then they had a little shop there. And yeah,
Oh, cool. I was just about
that's
to
where this
ask,
came
how do you
from.
make a scarf?
Yeah.
Wow.
So
looms.
this is handmade.
Awesome. That's really nice.
Yeah. Nice little diversion there.
There we go. Well, we do talk about African astronomy, and that was about Africa, so now we can get on to the astronomy part. Today's guest is Professor James Chibueze from the University of South Africa, UNISA.
Unisa, yes.
Yeah, it is Unisa.
Jacinta has this thing when she warms up her voice where she goes unique New York, and I thought that she just slipped back into that when she said Unisa.
It does sound like that. Unisa.
Unique New York. Unique New York.
There we go.
Yeah, can you say it fast?
Unique New York.
See,
Unique
it takes
New
some
York.
time.
Yeah, it is difficult. Okay. And our second diversion for the day. Back to business. So Jacinta spoke to Professor James Chibueze, who is at UNISA, as Jacinta mentioned, and he is a professor there. And I think we all know James, from the astronomical community. He's been around for some time and also is involved in many different things. Currently, I'm working quite closely with him with the organization of the General Assembly in August. He's leading the science committee there, so having regular meetings about that. I know you guys have also come across him in the past.
Yeah, I think one of the things that make James quite popular is the amount of work that he's done with young astronomers within the country, such as running the DARA project, which he did while he was a professor at Northwest University in
What does DARA stand for?
So DARA stands for Development in Africa with Radio Astronomy. So these projects have been currently going around in different African countries. I think the last one was in Kenya, but James ran one when he was still at the Northwest University in Potchefstroom. And it does invite a lot of students from across the African continent to come and do some astronomy projects, build stuff. I think at Northwest, they actually built some small radio telescope, which was really quite cool.
Yeah, I recently saw that DARA just got funded again for the next, I don't know how many years, but
awesome.
to quite a large degree. So
Yay.
There'll be a lot more DARA development
We should do a
projects.
DARA episode.
We should do
We
that.
should.
We haven't done one yet, have we?
Have we?
I don't think so. We must.
We shall.
Anyone from DARA who's listening to this, reach out to us. We'd love to do an episode with you.
All right. Jacinta?
Yes. So basically getting back to the chat I had with James, I found it super interesting. He's a hotshot radio astronomer in South Africa. He works a lot on VLBI, very long baseline interferometry, which is basically using radio telescopes all around the world, connecting them up so that you can get amazing angular resolution. So you can see very, very, very small regions with the radio telescope. And James is using this to look at small tiny areas in the Milky Way that are forming stars. And he's learning all about the physics of the formation of stars. And I asked him so many questions, and we went into a lot of detail. Sorry if it's a bit of a deep dive for you listeners, but I was fascinated because this is actually stuff I need to know in order to teach my students. And there was a whole bunch of stuff that I didn't know. So I was like, oh, tell me more about this. And so we did, was it a bit much? I don't know.
I must say that our listeners are looking forward to really an episode full of analogies. So these are things that you can actually imagine. Like, these are a lot of things that you can imagine and probably try.
Yeah, so stay tuned for, we do a lot of deep science explanations, but then wait for it, because then we're going to get to the,
The
afterwards we do the
analogies.
analogies. So, if it's not helpful, at least it'll be entertaining, I'm sure.
Maybe we can title this episode Acronyms and Analogies.
Yeah,
Maybe.
All right.
Yeah, and then James also talks about this, radio galaxies are what I work on. And, I thought this was the safe region where I was in my lane and James was in his star forming lane. But no, James decides to take over my lane as well. So he's also, into studying radio galaxies and why the jets are bending and magnetic fields and all of this stuff. So he tells us about some of his, his Nature paper, which if listeners aren't familiar with Nature, it's the kind of one of the holy grails of academia and science. And you really want to publish your paper in Nature. That's the highest quality journal. So James did that, and he's going to tell us all about his discovery. So what do you reckon? Shall we hear from James?
Yes, please.
Yes, please.
With us now is Professor James Chibueze from the University of South Africa. Welcome to the Cosmic Savannah, James.
Thank you, Jacinta.
I've been trying to get you on the Cosmic Savannah for several years. We did actually interview you several years ago, but there was something wrong with the audio and we couldn't use it. So I'm so glad that we finally got you.
Yeah, it's nice to be back here so I can say more things.
So we're not in the nice studio at the moment, but we are at a conference at the Soraya Bursary Conference. So that's the South African Radio Astronomy Observatory, which kind of runs Meerkat and some other telescopes. And we're here for, a nice long week conference with all of the students and postdocs who work on Meerkat. And this is my first time at this conference as a supervisor, but I'm sure it's not your first time. But James, before we get into all of that, tell our listeners a little bit about who you are, where you're from, what you do.
My name is James Chibueze. I'm a distinguished professor at University of South Africa, now leading a small group of radio astronomy students. We call it Astronomy Niche Area. Our focus is on doing SKA science, SKA square kilometer array. I'm originally from Nigeria. I did my bachelor degree at the University of Nigeria in the Department of Physics and Astronomy. So I have a first class in physics and then proceeded to do a master's degree in the same university and department in astrophysics. And then afterward, secured Japanese government scholarship, which is called the MEX. MEX is just a word for Ministry of Science, Culture, Technology of Japan. And the scholarship requires that you study in Japan. So which means you have to find a Japanese supervisor in a Japanese university, and you can only use that in the country.
Wow. So you did your PhD in Japan?
Yes, I did. Yeah.
Oh my goodness. Do you speak Japanese?
Yeah, I can teach astronomy and astrophysics in Japanese.
What? You can teach
Yes.
astrophysics in Japanese?
I did my PhD viva in Japanese.
Wow. Okay, that's deeply impressive. And now I have massive imposter syndrome. All right, well, that's awesome. Okay, so I know you've had this long and illustrious career ever since then, and yet you're about the same age as me, and I'm not jealous at all. It's fine. But first of all, okay, tell us about the experience of doing a PhD in Japan, and then also tell us what you were working on.
Well, the experience was good. I wanted to do radio astronomy because I had heard about the African VLBI network. This was just in the early days when it was being muted, that there will be a VLBI network that would spread the knowledge of radio astronomy to the rest of Africa partner countries for the SKA host bid. Yeah, so VLBI means very long baseline interferometry. It is simply using two or more dishes to observe the same source at the same time. They are separated by a distance, but in this case, you're thinking about a distance that is extremely long.
So this is two radio telescope dishes
Yes.
separated by some distance on the ground.
Yes.
But by a very long distance.
Yes.
Okay.
So like putting a dish in Kenya, for example, and another dish in South Africa, you would get a baseline, or the separation between the two telescopes will be roughly 6,000 kilometers. If you use that to simultaneously observe a source, you're doing VLBI. So I was keen to do VLBI, and I ended in Japan working with the famous Japanese VLBI network called the VERA. VERA means VLBI Exploration of Radio Astrometry. Astrometry is just how we measure distances to sources in the sky.
Yeah, there's a lot of acronyms in astronomy, right? It's so hard to say even one sentence without like 10 acronyms.
Yes.
So you went to Japan to start work, and it's related to the African VLBI network. So the fact that there is plans to put these radio telescope dishes in different African countries in order to combine with the eventual SKA telescope, and therefore to have very high resolution images, so be able to take really, really crispy images of the sky at radio wavelengths, right?
Yeah, exactly. So the idea was to acquire the skills from Japan and then use it in Africa. And that's exactly what I did. I did study star-forming regions within our own galaxy, places where the birthplaces of very big stars. When I say big stars, they are typically stars that are 8 times the mass of the sun and above. So if you imagine the sun being 10 to the power 30 kilograms in weight, I'm sure you can, it's almost unfathomable. Then if you multiply that by 8, that's the size of the smallest massive star we know. Anything less than that we'll consider to be intermediate mass or low mass star.
Okay, so the sun's an intermediate or like small
It's
guy.
a low mass
It's
star.
a low mass because it's just a
we
little
actually-
teachy one.
We actually call it a yellow dwarf in
Oh, a
astronomy.
dwarf, really?
Yeah, so I studied how big stars are formed, going all the way from the gas and dust in a cloud that make up the star. So because they are nearby, well, you would want to have very high angular resolution to see all the details of the motion of the gas. So VLBI will give you that resolution because you have a very huge separation between the antennas or the telescopes. So your angular resolution come down to milliarc seconds level. Don't worry, I will explain that soon. When we look at an object, what we actually see is in angles.
On the sky, right?
On the sky. Yeah. And if you imagine 1 degree to be very small and you project 1 degree to a very long distance, that becomes a huge chunk of the sky. And you can have hundreds or even thousands or hundreds of thousands of star-forming region within that small space.
Really?
Yes.
Within this tiny, tiny little patch of sky?
Yes.
Wow.
So typically you would have 1 degree is equivalent to 60 arc minutes, and 1 arc minute is equivalent to 60 arc seconds.
Okay, so like a clock, and you've got 60 minutes,
Yes.
and that's in one, we call it a degree, but in this analogy, it would be an hour.
Yeah.
And then you've got 60 seconds in each minute, right? And so we split the sky up in terms of angles, and we split those angles into degrees, into minutes, into seconds. Okay,
Yes,
so
exactly.
so an arc second is the smallest unit there, right?
Yeah,
That's
so-
tiny.
So even within an arc second, you can have at least 10 to 100 massive star-forming objects.
Whoa.
So, which means we need to go even further to break down 1 arc second to smaller scales to be able to study one of those star-forming regions or star-forming cores in details.
Okay, and so like just for comparison, if you put your thumb out as far as it goes and you point it up at the night sky, that's about what, half a degree?
Yeah, roughly half a degree.
Okay, so that would be 30 arc minutes, which is 30 times 60 arc seconds. And you're saying that there's hundreds or thousands
Yeah.
of star-forming regions within an arc second.
Yes.
Wow. Okay, so lots and lots and lots and lots.
Good. So we need milliarc second scale, which is 1,000th of an arc second, and even micro arc second scale, which is 100, well, about a millionth of an arc second scale to find details of the gas structure and gas motion. That's why we need VLBI.
Okay, so we've got arc seconds. We understand what that is now. And then we're breaking that down even smaller into milliarc seconds and then smaller into micro arc seconds. And there's a million microarc seconds in 1 second.
Yes.
Okay, so we're looking at a teeny patch of sky.
Good.
And to do that, we need a telescope with extremely good resolution.
Absolutely. So
Okay.
that's why you need
And
very
that's
long baseline.
VLBI.
interference. Yes, that's why
Okay,
you
so
need VLBI.
so we need to make the size of our telescope basically the size of the Earth, right? More or less.
Yes, we do have that already, as you know. We have what we call the global VLBI network that you can achieve a baseline of about 11,000 kilometers, which gives you an excellent resolution to study objects.
Okay, so now let's talk about the star-forming region. So as the name suggests, I'm going to assume it's a region
Yes.
in the Milky Way
Yes,
where stars are forming.
exactly.
Good, I nailed it.
Yes, absolutely.
So explain to me what is in these star-forming regions.
So if we're fortunate to be in South Africa, where you can go to some dark areas and you look at the sky and you'll see the Milky Way with your own eyes. If you look closely at the Milky Way, you will see bright spots, which are just regions where you have middle-aged stars that are shining and giving out light. But you also find a bunch of dark lanes. Those dark lanes represent regions where we have a lot of dust.
So it's like the dark patches in
The dark patches you see
along the Milky Way.
Yeah, exactly. So those are the natal. By natal, I just mean regions where the stars are born.
What do you call it? Nettle.
Yeah, like star-forming regions. Natal.
Oh, like natal, like as in, where something's
Birthplace,
born.
yes.
Birthplace.
Yeah.
Got it. Cool.
Yeah.
So these dust lanes are the birthplace, okay?
Yeah. So the dust we talk about are just similar to the dust we see on the surface of the Earth. They are mostly carbonate materials and silicate materials. They are produced mostly by dying stars, and then they are recycled and used again to form new sets of stars. So the dark lanes are just because you have dust particles and everything shining from behind it. The lights coming from the back are all absorbed. Just think about it that you're driving behind a rickety vehicle that is chunking out black smoke.
Okay.
Your visibility will be obstructed due to the black smoke, not because the objects ahead are not reflecting light, but because the light reflected by those objects are absorbed by the dark smoke produced by the vehicle ahead of you. Then you don't see anything.
So that vehicle may have its lights on and have bright brake lights,
Yes.
but you're not going to see it because
See it.
of the dark smoke, and then you might ram into the back.
Exactly.
But that's where the analogy ends.
Exactly.
Okay.
Exactly. So that's what we see in the Milky Way. But those are really crucial parts of our galaxy because that's where all the new stars forming within our own galaxy are being born. So typically you have gas and dust mixed together. They're typically extremely large. Their masses are as big as sometimes thousands, hundreds of thousands of solar masses. We use solar mass in astronomy to describe the mass of the sun, and we use that as
A unit.
Yes, a unit
Yeah.
to classify other more massive objects.
Oh, so like a measurement. So it's like 100 to 1,000 times the mass of the sun.
Yes.
Yeah.
And mass of the sun is 10 to the power 30 kilograms.
Okay.
Good. So in these regions, the distribution of the gas and dust is not uniform. It's not homogeneous.
So it's all clumpy.
It's a bit clumpy. And therefore, gravitational law will kick in because you have substructured materials that are of different masses, and therefore they can collide and...
Right, because the more mass, the more gravity.
Exactly.
So then if you've got regions that have more mass because it's clumpy, they're going to have more gravity. So then stuff's going to fall into that region and get more and more dense, right?
Exactly. So if you have gravitational collapse, you start forming things like high density cores.
Is that called a Bock globule?
No, that is called cold cores.
Okay,
in
cold
Stafford.
cores.
Yes,
I'll
because
try.
they are extremely low temperatures. They're
Okay.
typically between 20 and 30 Kelvin.
So you said about 20 to 30 Kelvin, and then that's very cold. What does that mean in like degrees Celsius?
So 20 Kelvin is equivalent to minus 253 degrees Celsius. That
Okay.
is extremely low
Very
temperatures.
cold. Very, very, very cold. Okay, so like way colder than it gets on Antarctica or anything.
Exactly.
Okay.
You need that cold temperatures because the dust need to be so cold that the gas gets frozen onto the dust.
Oh.
Therefore, when a star starts to form, you have high density in the core, there's a lot of collision, the temperature starts to rise.
Oh.
The increase in temperature impacts, the dust will absorb the photons or the heat that comes from increased temperature in the middle, and the gas that is frozen onto the dust grains will be released.
It like evaporates. Okay.
And then we can detect it because the release of the gas means that they will generate radio waves, which you can detect with telescopes.
Really?
Yes.
I did not know that. This is so exciting. Okay, as you can tell, I study galaxies and I know nothing about this. But interestingly, I do have to teach galactic science. So I'm glad that we're all learning something today, and I'm probably going to tell my students to listen to this episode.
Yeah, that would be cool.
So hi to my third years if you're listening to this in the future. This is where I learned it in the first place. Okay, so you've got in these really cold cores in these star forming regions, you have this really, really cold area. You've got gas that has now like frozen onto dust particles, and which is basically like thick smoke.
Yes.
And then once it gets dense enough, it starts to heat up.
Yes.
Because of like these particles are starting to collide with each other.
Yes.
And then the gas evaporates, and when it releases off the dust, it emits a signal.
Yes.
It like emits some radio light,
radio
which we can
waves,
pick up.
yeah.
So why does it emit radio waves? What happens there?
Well, every molecule, of course, atoms, for example, hydrogen atom neutral hydrogen would emit when you have a change in spin direction of the electron and the proton. So their direction typically spin the same direction, but if you have a change in the spin direction, it releases radio waves.
This is like a weird quantum property of electrons and protons, which doesn't really have an analogy in real life, but we just call it a spin direction.
Yes.
Yeah. Okay.
Yes. So in the case of molecules like carbon monoxide, which is one of the simplest one, the bond between the carbon atom and the oxygen atom is not static. It does vibrate. Okay? So we have vibrational state of emission, which is for vibrating molecule. There are also molecules that we call polar molecules, that like ammonia, which have one atom of nitrogen and 3 atoms of hydrogen. This has some angle. It makes some kind of angle that you can trace. You can cut into 2, and then you have a symmetry. Such molecules sometimes rotate.
Okay.
So we have rotational transitions, and those are transitions, emissions that come due to the rotation of the molecule.
Okay.
So you have vibrational emission and you have rotational type emission. One molecule can have multiple of these depending on the conditions of the environment.
Is this called row vibrational?
Yes.
Transitions? Yes, I nailed it. Okay, so this is exciting because I learned about this recently when I had to teach this course, and I had never heard of this before. So molecules can vibrate, and that emits light, and they can also rotate, and that emits light, and they can rotate and vibrate at the same time, and that emits light.
Yes.
Cool. All right. And so then that's emitting this light at, I'm going to assume this is what, millimeter wavelengths, sub-millimeter wavelengths?
We can also find some spectral line at centimeter wavelengths.
Okay, so radio telescopes, millimeter telescopes, those sorts of things.
Yes.
Okay, cool. All right, so you're studying these star-forming regions. You're studying these molecules that have just been released from the dust and they're starting to vibrate. I know this is getting a little bit further away, but like, what happens next? How come it starts off as this cold, cold, cold region? How does it suddenly get to like really hot and start forming stars?
So the star continues to accrete. The beauty in looking at star-forming region is that you find something super interesting, which is that the star continues to swallow up more gas to grow in its mass. And at the same time, it does spin around, so has some angular momentum, which you cannot sustain. Like, you can't keep spinning
faster and faster infinitely.
without releasing some of that angular momentum away. Otherwise, you have a catastrophe. So let me put an analogy. If you pick up a string and tie, say, a stone to one end and hold it in your hand and spin it around, if you spin it endlessly, you're generating angular momentum that needs to go away, but you're keeping hold of it in the system. You would realize that if you spin it for 100 years, even if you've used a metallic string, that is going to rip off.
Right.
Okay, so the angular energy you generate needs to go away, otherwise it becomes very destructive.
Right.
That happens in star formation. The core is spinning around and has a disk and is accreting material as a result of the spinning process. We call it accretion. However, it cannot continue to accrete without taking away some of the angular energy.
So when you say accrete, it means like grow bigger and eat more stuff around it. Yeah.
So it eats more stuff, but due to the spin, the angular momentum you generate, you also need to give out.
You have to lose energy somehow.
Yes, you have to lose the angular energy somehow. So forming stars launch what we call outflows through the poles. So around the plane is the disk, which is typically fairly thick, but from the poles, well, it does eject material all around in three-dimensional shape. But around the disk, you have some thickness, and therefore it's difficult for things to escape from there. So you see things escaping from the poles.
Okay, so if you think of like Saturn, which has a ring around it, that's like the disk area.
Yes.
And then the poles would be like directly above and below, like
perpendicular to the disk.
The North Pole and the South Pole of Jupiter perpendicular to the
exactly.
disk. Okay.
So
sorry, Saturn. Did I say Jupiter or Saturn? I meant Saturn. Saturn has a ring, okay.
Yes. So we call that bipolar outflow.
Bipolar outflow.
Yes,
okay.
because it goes out through the North and the South Pole, and the disk is around the perpendicular direction. So you will see this in many star-forming regions, and that's one of the things we use to identify a forming star. We know it's in the early formative stages, and it would have that accretion disk and will have bipolar outflow. And my study was focused on using high-resolution image to look at the inner part of the outflow to find those extremely collimated gas that is just being ejected by the star. And it was in my time we discovered that the outflowing material is actually spinning around and going outward.
Oh.
That is evidence that the angular momentum from this rotation of the disk is being carried away through the outflow, therefore the star can continue to feed.
Oh, wow. That's so cool. Let me guess. Is this called a precessing flow or something?
It's slightly different from precessing.
Okay.
Precessing is part of it to some extent. Precessing is when you do, okay, now I need to demonstrate.
Okay, now you need to do this visually. Okay,
Yes.
so James is like moving his arm in a twisty, weird
Yes.
way, which I have no idea how to describe that.
So if you watch these movies where people try to spin around a stick in a fancy way where you can rotate it around, so the outflow is not just stationary, it just keeps turning
Okay.
in this rotating direction. So sometimes you see it here, on the other time, this northern side.
Okay.
The northern side of the outflow is to the left or is to the right. It just keeps going.
So imagine, like a what do you call these things? A spinning top?
Yes.
You know, when you turn that.
Yeah, when it's about to.
And when it's about to topple over and it like
then you
starts to
see it.
wobble.
Exactly.
Oops, I hit the microphone with excitement. So it starts to wobble because it's like, it's
that wobble part
the stick part is wobbling.
Yes,
Yep.
that's the precession. So you consider the wobble of the stick as precession, but the
spinny
circular
bit?
is actually the angular momentum, the outflows carrying the angular momentum. So that's a good example.
There we go.
Perfect.
There we go. That was teamwork. We've
Yes.
come up with a great analogy we should
Yeah.
always use from now on.
Yeah.
Processing jets and spinning tops. There we
Yes.
go. Cool.
Yes.
All right. So just to summarize all of that, you've got this like cold region and inside it, the gas is starting to evaporate and now it's triggering hydrogen fusion. So the fusion of two hydrogen atoms. No.
Not yet.
Okay, so it hasn't started that yet.
So we started from dense cloud,
Dense cloud.
inhomogeneous in
Yeah.
densities.
Yeah.
And then we went all the way to gravitational collapse.
Okay, so now it's getting like this runaway effect almost of like getting denser and denser and denser, where more and more matter of more of this dust with a frozen gas onto it is like clumping together.
Exactly.
And it's getting really clumpy. And as it's doing this, it's rotating. Okay,
Yes.
It has what we call angular momentum, which is just movement in a rotation direction.
Yes.
So it's rotating, and as it gets more and more and more mass, it's rotating faster and faster. But what you were saying was that you can't get infinitely fast. It can't rotate infinitely fast. So it has to lose energy somehow as it continues to like what we call accrete or like get more material like spinning together. And we didn't really know how it lost angular momentum in the past.
Yes.
But during your PhD, you figured out that it's losing it through these what we call outflows, where there's some kind of, is it gas or is it light or is it dust? It's gas. Okay.
Yes.
So there's gas being ejected out of the poles, out of like the North Pole and the South Pole of this like protostar, I guess.
Yes,
It's a star that
protostar,
hasn't started being a star yet.
Yes.
Baby star, or like fetus star.
Yes.
And then you found with this VLBI, so like very high resolution astronomy, you found tiny little wobbles in these outflows, and that proved that that's how the angular momentum is getting lost. That's how the energy is getting lost.
Yes.
And then therefore we don't break physics.
Yes. So you continue to follow physics law, which means you don't keep the angular momentum in the system infinitely. You're able to carry it away from the system, but the angular momentum is not stored in the system infinitely. So you need to carry it out of the system to some extent so that the star can continue to accrete and grow in mass. So technically, what stars do is the same thing humans do. We eat, we excrete, we grow.
Okay.
So you cannot excrete more than you ate.
Mm-hmm.
So stars accrete material from its environment, from the available reservoir of gas and dust, but they also excrete by ejecting some of the materials in bipolar outflow.
Cool.
But the outflow rate is lower than the infall rate or the accretion rate.
That's why it can still grow.
Then it can still grow in mass. So this will happen for high mass stars. One of the key interesting thing is that their evolution is very fast.
They live fast, die young, right?
Yeah, big things live faster life and die quickly. So compared to the sun, which is about 4.5 billion years old, massive stars will evolve within a few million years. That is really very short. So they still stay in accretion phase and they start burning hydrogen and they keep accreting. But the accretion rate is so small that compared to the combustion rate, and then they can exhaust the hydrogen so quickly and they expand and then suddenly explode in supernova explosion and die.
Oh, right. Because we're talking about high mass stars, right? So we're trying to form stars. We're talking about stars forming, and these stars are many times bigger than the sun. All right. So if the sun was forming, then once it starts rotating and it's forming, then eventually it stops growing.
Yeah.
Right. It kind of like blows all of the neighborhood material away.
As soon as it starts to burn hydrogen, the radiation pressure is too strong. It blows away the remaining formation material, and you will have a star that is shining on its own. There will be a few particles of dust around the disk, but the rest of the gas is mostly blown away.
And those particles form planets, right?
Exactly.
Like the Earth.
Yes. Yeah.
Sorry, I stole your mic drop moment. I was just too excited.
No problem.
Okay. All right. But then the high mass stars, they don't blow this material away yet. They keep accreting. They keep growing.
Yeah, that's the mystery behind high mass star. We don't know why. Even when they get into main sequence and start burning hydrogen, they still continue to accrete. This is still a mystery. We don't know why.
Okay, so they're no longer baby stars. They're real stars now. They've become real stars. They started burning hydrogen, but they're still growing.
Yes.
And we don't know why they're still growing.
Yes.
Ah, that's cool.
So if you solve that problem, you would have solved one of the big problems of astronomy.
Nobel Prize.
Maybe. Yes.
I wouldn't put it past you. Okay, so then they continue to grow. They end up as these really massive high mass stars, and then because they're burning their hydrogen so fast, they just run out of fuel really quickly, and then they explode in big supernova explosions.
Exactly.
Okay, cool. Okay, so I think that we'll have to stop the discussion of high mass stars there because I have so many questions, but I think I'll keep asking you once we turn the recorder off because we're getting into a lot of detail, and I don't know if the listeners have already stopped listening. Sorry if you have. But speaking of big discoveries, I want to completely jump topics now because I know you have to run away in a minute. And I want to talk about the holy grail of astronomy and our careers is trying to get a paper published in Nature or Science. These are the big journals, the really like famous journals. And it's like, once you do that, your career's set. Now, James, I happen to know that you recently had your very own first author paper published in Nature.
That's correct.
Congratulations.
Thank you.
All right. So tell us what this paper was about.
Okay, maybe the background of the story is moving away from high resolution with VLBI after my jobs in Japan and back home in Nigeria for a short while, and then to SKA, and then to Northwest University, and before moving to UNISA. I realized
as a brief summary of all the career along the way. Okay.
Yeah, so coming to South Africa, I thought, okay, there is no VLBI network. Of course, the African VLBI network is still up and coming along, hopefully well enough. But the Meerkat is an excellent instrument. Fantastic sensitivity. I mean, going down to what we call 4 microjanskis per beam.
What does that mean?
that simply means that you can detect
very faint
radio signal.
Yeah.
I'm trying to find a good analogy. That could be equivalent to detecting the power generated by a single snowflake on the surface of the moon.
Wow. Okay.
So that's how sensitive Meerkat is, and I just could not go past using such instrument. However, the resolution is not as good as
VLBI. You're a bit spoiled there.
Yes, I agree with you. I was spoiled for resolution. So if you have poorer resolution, you want to go to things that are further away. That's how I started off to look at other objects. The principles are the same. It's the same interferometry. So I started looking at distant objects, extragalactic objects, which Jacinta will be very happy to hear that I do now.
Yes.
And
now we're getting into my field.
Yes. So I managed to look at an object that is called Ebel 3376. This is a cluster of galaxies. There are 2 of them that are merging together. And they do have one very bright radio galaxy that shows an interesting morphology. So the original science idea behind the proposal that I submitted to do Meerkat observation was to look at how particles are reaccelerated at the edges of a galaxy cluster. So we have something you call radio relics. It's just radio emission generated by particles at the edges of the galaxy clusters that are reaccelerated by energies coming from the center of the galaxy clusters.
Okay, so you've got a cluster of galaxies, so just lots of galaxies clustered together, as the name suggests. Mm-hmm. And then you've got between these galaxies, you've got like a soup of hot gas. Right?
Yes.
And that gas is obviously made of particles.
Yes.
And you've got electrons in there as well. And, they've got electric charges. And then for some reason, these electrons are getting a big boost and they're starting to move really, really fast. And they're releasing some radio light as they do that.
Yeah.
And so we want to understand why they suddenly get this boost.
Exactly.
Okay, why do they get this boost? Do we know yet?
We do have an idea. We think the reacceleration of the particle, the energy you need to do that come from the center of the emerging galaxy clusters. So that was the original science goal. But when I made the images from my Meerkat observation, I found a galaxy that looks extremely strange.
Extremely strange.
Yes.
Okay.
So radio galaxies, or what the experts call active galactic nucleus, is just a galaxy that is launching these fast jets from the poles. Mm-hmm. Remember I talked about outflows, bipolar outflows. The jets are also bipolar. They go from the poles. The disk of the galaxy is usually perpendicular to the jets.
But they're originating from a supermassive black hole.
Yes. We actually have a name for the black hole, or the galaxy that I refer to is MRC 0600-399. That's very technical.
Well,
I know,
that's a very interesting name.
Yeah.
Not really.
So typically what you find of radio galaxies is that they have 2 lobes of jets, one to the North Pole, the other one to the South Pole of the galaxy. But in the case of the second brightest galaxy member in the cluster I observed, it had a U shape if you turn U clockwise by 90 degrees.
It makes a C, sort of.
Yes, sort of C.
Okay.
That's what it looked like.
Okay.
And
She found like a C-shaped radio galaxy.
yeah, that's so weird. So if you stretch out the ends of the C and it stays in a straight line, that's how weird it was. So which means that the jet is launched perpendicular, going north-south direction, and then bent by 90 degrees to the left.
So it's almost like if you put your hands out from your shoulders, you put your arms straight out in either direction.
Yes.
And now you bend your elbows.
Exactly.
So that your hands are kind of perpendicular to your arms.
Exactly.
And now you're making this weird U shape, but it's kind of a C-shaped thing.
Yes.
So that's what the jets of this radio
That's what it
galaxy
looked
look
like.
So they're
Yes.
meant to shoot out directly from your arms, straight
Yes.
out. But then they were doing that. And then for some reason, the end of them bent. In a weird 90-degree angle. That's so strange.
Yeah, that is very strange. So if you look at that image and you're an astronomer, the first thought will be, well, the north-south moving lobe of the jet is definitely from the black hole. Okay? But the bend direction could be something else. So maybe there is another galaxy lurking in the background that you are seeing the jets from. So my first job was to look at, hey, what is this? Is there any other galaxy within the vicinity? And I looked through all the other wavelengths. There was nothing.
There's no other galaxy.
No other
Okay, so
galaxy.
there's no other galaxy interacting with it, causing some weird bending.
Yes.
Can I guess something?
Yes.
Yes. So because this is my field, I always look at these weird radio galaxies.
Yes.
But a lot of these bending is because the galaxy with the black hole in it is moving through this like hot intracluster medium, the hot soup within the cluster.
Is that what you guys call ramp pressure?
Yes.
Okay, good. So that was what everyone would guess.
Yeah, and it's like
But-
blowing the jets like in
Good.
this direction.
Let me surprise you. Why?
Okay, so it's not that. Okay, all right,
So
I'm
let
interested.
let me surprise you. The bending direction of your arms, of your elbow,
Yeah.
is rather moving against the ramp pressure direction.
Wait, what?
Yes.
So we know that there could be some ram pressure. So it's like, if I can give an analogy of my own,
Yes.
if you're swimming in the sea,
Yes.
that's like you're swimming through this hot gas that's between the galaxies in
Yes.
this cluster, right? And I happen to have long kind of thin hair, which is like soft. And so if I'm swimming through it and my hair's out, it's all going to be swept backwards off my
Backwards,
head.
yes.
That's like the equivalent of ram pressure,
pressure,
right?
yes,
So it's like
yes.
my hair is all streaming backwards.
Backward.
So it's like the jets should go streaming backwards
Yes.
as it's moving through
But rather
this.
in these jets,
But now it's in the other direction.
your hair is
It's
swimming forward.
forwards. Can you imagine swimming
against the ramp pressure?
swimming through the sea and your hair's going forwards in front of your face? That doesn't make any sense.
Yes, there is more to it.
Okay.
So first, the jet is bending against ramp pressure, which is unexpected. And second, if you have ramp pressure pushing against your hair, you cannot keep it streamlined like you plaited it or you braided it. But these bent jets actually stayed collimated for more than 100 kiloparsec scale.
What? So they went straight out from your shoulder to your arm, and then they bent, but that bent bit also stayed straight
Stay straight and collimated.
and collimated, like staying in like a really straight, like pencil shape.
Yes.
What?
For-
Dude, that is so weird.
Yeah, so that's not all.
Oh, there's more. Wait,
Yes.
there's more.
So in the bent arm that you have, there is also some tiny bit that came backward.
Okay, so James is pointing to his elbow. He's got his arm bent. And he's pointing to his elbow, and he's making his hand go away from his elbow in the opposite direction of his arm.
Yes.
So there's an extra bit at the back.
Yes.
You've got like an
There's a-
extra hand at the end of your elbow.
Yes. If you
What?
watch Japanese animation, there are a couple of animation that has, I don't recommend it. It's a violent animation. They have a sword that points, it's like a hook, but it has a hook in the front and some small pointing backwards. So,
Okay.
So that is, if you look it up in the dictionary or just put it in Google and see a picture, it's called a scythe.
A scythe.
Yeah.
Ah, yes.
SCYTHE.
Okay.
So we called the morphology we saw in the bent radio galaxy a double scythe structure.
Oh, cool.
That's where we got the
That's
name.
where you
It was
got the
inspired.
word. I was
Yeah.
wondering where that came from.
Yeah.
Double scythe. Okay,
Yeah.
so you've got this weird U-shaped jet thingies with a scythe, like extra point at the back of
Backward.
it. Okay, James, come on. You gotta tell us now. What is this thing and what's causing it?
Okay, cool. So now it's obvious it's not ram pressure, because if it was ram pressure, you should bend your elbow backwards. Okay? And then, of course, in the case of ram pressure, you get what the extragalactic people like Jacinta call WAT. It means wide angle tail. It just means that the tail of the radio jet makes a plume shape, okay? Spreads all over with wide opening angle. This one stayed very collimated.
Okay.
So you can no longer explain it with ram pressure, which is your favorite. Then you have to start exploring what exactly is going on. So, well, one thing you can think about is the presence of magnetic field.
Magnetic fields,
Yes.
always the culprit.
Yes. Yes. And in our case, yes, we use the X-ray data from XMM Newton telescope. That's a space telescope that can observe sources at X-ray wavelengths. And then we looked for what we call discontinuities or cold fronts in the X-ray distribution. If you find a cold front, just regions where you have the densities of the X-ray photons to be different from the density profile of the rest of the environment, then we call that a cold front. So what we realized from X-ray data is the point where you have the bending of the jet, there is a very strong magnetic field, which is a cold front detected at X-ray wavelengths, which means there is strong magnetic field that the jet hits perpendicular to that direction. Complex.
That's complex.
Yes.
That's really weird.
You really need to see the pictures.
Yeah, wow. Okay, listeners. So there will have been no breakthrough there, but we just took a pause. And James showed me the simulation that he made, simulating these magnetic fields and these radio jets and what he thought happened. And I'm going to try an analogy. And then James is going to tell me whether it's ridiculous or not to try and explain this.
Cool.
Okay. So imagine you're camping. You're in a tent. And the roof of your tent is a dome. Okay, so it's like curved. It's not one of those pointy ones at the top. It's curved, all right? And in the middle of the night, you stand up and you forget where you are. And you're a tall person, all right? So you stand up really fast and your head hits the roof of the tent, right?
Yes.
And then you go, and then you bend forward as your head hits the tent, right? And as you bend forward, you throw one arm out behind you, right? That's kind of what's happening.
Yes.
So you're the jet. As you're standing up, that's you going out in the perpendicular direction where you're meant to be going. And then the dome of the tent, that's the magnetic field. That's the direction that the magnetic field is going. It's like this dome structure over the top of you. It just happens to be there for whatever reason. As you stand up, you, the jet, your head hits the magnetic field and it makes you curve forward and straight out. And then you've thrown your hands back to balance you, and that's the scythe bit.
That is very fantastic. I mean,
Yeah.
I could never have thought about that.
Yes.
That's so good.
I nailed it.
Yeah, you did. And I can just add, we know where the magnetic field comes from. There is magnetic field everywhere. But in the merging process of these two clusters, you generate a subcluster material that is traveling through the medium.
Okay.
And this will compress the magnetic field lines.
Okay, wait. Say that again.
You have subcluster material traveling through the center of the cluster. As it moves, it compresses magnetic field lines.
Okay.
And what we call it's like wrapping around the magnetic field lines through the traveling subcluster material.
And that's where this
that
dome
compresses
thing. Okay,
this
gotcha.
magnetic field, and it becomes stronger.
All right. Okay.
Yeah.
Okay. So you've got inside this cluster, it's clumpy, as we talked about in
Star-forming regions.
Star-forming regions. It's clumpy, and so you've got some areas that are more dense than others. And as this, what we call substructure, the denser region, it's traveling through the rest of the cluster. It's kind of making the magnetic field twist around it and warp and kind of end up in this like
Strengthen.
in this kind of dome shape.
Yes.
And that's why there's this curvy magnetic field. And then when this innocent little radio galaxy just happens to send its jet out in that direction, it gets curved in all these weird directions when it hits the magnetic field.
So that magnetic field explains why you can still keep the electrons emitting the radio waves, okay? Keep it very collimated, not spread all over the place.
Not spreading out.
If the magnetic field lines were not strong enough, you cannot keep that electrons collimated. They will fly everywhere, and you have what you typically call wide-angle tail galaxy.
Right, okay, so it hits the magnetic field, and the magnetic field lines say, come along this way, electrons. We're going in this direction, all of us, in a nice line.
Yes.
Everyone hold your hand of your partner. We're going in this direction. Don't get lost. Okay, cool. I love it.
Yeah.
All right, James, look, we've talked for ages and ages. That was so exciting. Thank you so much for all of your time. This has been really awesome.
Yeah, it's always nice talking to you.
All right, so do you have any final messages for listeners before we go?
This is the best time to be an astronomer. For the young people who may be listening to this, trust me, I am jealous of all of you because if we could do this sort of science we're able to do with the current instruments and knowing the sort of instruments coming up in the next decade, I am super, super jealous of you guys. It is an opportunity you should take. Take it away, run with it. There are bursaries available to study astronomy. Take your studies seriously. For those in high school, please try and do maths, physics, and chemistry. Do a bit of computer science. And I look forward to seeing you guys sometime in astronomy.
Oh, that's awesome. Thank you so much, James, once again, and congratulations for everything.
Thanks a lot.
Bye.
Bye.
Oh, that was such a great interview. I really enjoyed it. I learned so much.
You were right. You did go into a lot of detail.
Yeah. But it was interesting, right?
It was interesting. And I mean, also, I think to start with, just to hear about James and the story where he's come from, I think that all of our minds were completely blown to hear that he did his PhD in Japanese in Japan.
His Viva, and he lectures in astrophysics in Japanese.
Yeah.
It's wild.
And I was just thinking about the two of you. Like, if you could teach astronomy in any other language than English, what would it be?
What I would want to teach in or what I could teach in?
Okay, let's do both. What you could teach in and what you would like to teach in.
I'll do what I can teach in nothing. I'm embarrassingly monolingual.
I mean, I'm basically monolingual too. I think that my best second language would probably be Spanish. And then, I mean, I did Afrikaans and Zulu at school. But, I don't think I could even begin to stand up in front of a crowd.
I've tried to explain my work in Croatian. I used to live in Croatia.
Yeah.
I can confirm it is extraordinarily difficult. Like, hats off to James. I have no idea how he could do
wild.
that. That's amazing.
Yeah. I thought that was really fascinating that he could do that. And it's just one of those things when learning the science and learning the language just come together again, which is similar to what we heard from Zara as well when she came into South Africa.
Yeah, true. Because, she knew Malagasy and French, and now she, teaches in English. What about you, Tia?
Well, I'm not monolingual. But I could probably try to teach in Setswana. I think I can give explanations in Setswana.
Analogies.
But I always have to actually understand what it is first in English and then try to bring it there. And only now I'm actually learning other words in Setswana that I didn't know because I grew up in Soweto. But my grandmother is from the Northwest. So sometimes I ask her about these things and she just has a different language, like a different word for something I grew up with knowing. But now I see why that word would make sense, especially in the context of astronomy or explaining stars and galaxies and things like that. So I think Setswana. I'd take Setswana. So the other thing about the analogies and the deep dive explanations showed that actually Jacinta is such a great teacher.
Oh, thank you.
So, do not necessarily say, oh, I just know a little bit. But, just through your explanations, we could also get to see how much you understand your stuff. So I think that was also kudos to Jacinta in this episode because well done.
Oh, thank you. I did not expect that. Did you like my tent analogy?
I did.
I did.
Thank you, Jacinta. I think you did a great job with that interview.
I liked the analogy because when I was listening back to this chat with James, we had this chat quite a long time ago and I'd forgotten what it was about. And when he was explaining the C-shaped radio galaxy and like the little extension out the back, I was like, I can't picture what he's talking about. And I didn't remember doing the analogy. And then it came up to that bit and I was like, oh, that makes sense. Now I can picture it.
So you came up with the same thing twice.
Yep. And also I had completely forgotten that James did his PhD in Japan. And then when he said that, when I re-listened to the recording and he said that, I was like, oh, really? And then me on the recording said, oh, really? Oh, wow.
Your neural network's quite predictable.
Who knew I'm very similar to myself? Anyway, so yeah, I thought that was a really interesting episode. Lots of new physics that we haven't talked about before. But we have talked about something similar with Stabile Kolwa in episode 63, I think it was, talking about, formation of stars and also radio galaxies and, all of this kind of chemical changes going on with molecules and vibrating molecules and all that sort of stuff. Yeah. I guess that's the end of the science bit for today. So how are you, Dan?
Pretty good, thanks. I am doing my big ultra marathon, which you guys kindly put on the website as my hobby.
Yeah, we've been updating the About Us page on the website. Thanks, Shaman, for he's the one who's been leading that. And we needed some more spice, so I added in our hobbies.
So that's my spice for the weekend.
When is it? It's coming up this weekend, right? Coming
up this weekend at time of recording. Yeah.
Are you ready?
I've got to be, hey?
Yeah. How intensive is the training for this ultra marathon?
Pretty intense. I've been a pretty grumpy and hungry and tired person for the last 6 to 8 weeks.
Wow.
But I'm emerging from that now, and now I'm friendly and happy again.
Wow, are you still off coffee?
I am off coffee. This is a problem. Yeah. Yes, a few more days of being off coffee, and then I'll be back on it hard. We don't want to get into like the science of sport here, but basically just trying to maximize my caffeine kick on Sunday morning.
Mm-hmm.
We'll be cheering for you. I'll watch on TV.
Oh, thank you. Yes, I think we have mentioned it before that this is a bit of a big deal in South Africa.
No big deal, but it's massive.
Everybody stops and watches everyone run from like city to city on a Sunday morning.
Yeah. Unfortunately, it's before my awaking time.
It's the whole day, Jacinta. It takes people 12 hours.
No, but Dan, I'm sure you're very fast and you're going to be, up ahead, and I'll have only just woken up and you'll have already passed the
It'll
cameras.
take like 5 hours.
No, not quite.
Just remind the listeners, how long is an ultra marathon?
This one's 87.
87 kilometers. I don't even know if that's possible, but good luck.
Well, you can watch on TV and then you'll understand.
Yeah, that's true.
I'm joking. Who's next?
Simiso.
I'm next.
How are you?
I'm good. I think today I'm really good today because yesterday was such a good day for me. Like ticked off things on my to-do list.
What does that even feel like?
I don't remember. So good.
Oh my word. So I feel like now I'm finally again just at a right place, like where I can now do stuff as they come. So that's really great. And then, that's just it. Like I'm good. I'm okay.
Nice.
No complaints.
Awesome. What a place to be.
Very nice. Yeah. Enjoy it.
For the week.
The day even. Who knows what tomorrow holds.
Enjoy the moment. Seize it.
And how are you, Jacinta?
I'm good, thanks. Yeah, everything's, actually, for the moment, the last few days, not too crazy.
You or your life?
Both.
Okay.
More the latter than anything. I had a little adoption party for my dog Sam on the weekend.
Nice.
Sort of also to raise money for the local dog shelter where he came from, Wolf Project, Oscar's Ark. So if you'd like to donate, maybe we'll put a little link on our website. And it was really great. We had it in a dog park. Sam had a great time running around with all the dogs, and there was lots of human friends as well who were playing with him and giving him treats and everything. So yeah, it was a lot of fun. And what have I been doing science-wise? Actually, I have been doing science.
It's a shocking day today.
I know. You would think it wouldn't be so shocking since it is my full-time job. However, yes, I've been sitting with my students and actually doing science work with them, and it's very exciting. Reminding me, why I love my job, and we are almost ready to publish a paper. One of my students is ready to submit in about a week, hopefully, or 2. And
so a nice result. Should we speak to them on the Cosmic Savannah?
We should. Yeah, we will. In fact,
in
July. July, we will do an episode on that. And I'm just preparing because shortly I'm going to be going to the UK for a month, mostly for work, and taking my whole research group with me. So
That's exciting.
Yeah, looking forward to that. And we'll record some episodes from there.
School tour.
That's cool.
Yeah, so, sort of. Awesome.
Okay.
Okay.
And I guess that's it for today. So thanks very much for listening, and we hope you'll join us again for the next episode of The Cosmic Savannah.
You can visit our website, thecosmicsavannah.com. We will have the transcript, links, pictures, and other stuff related to today's episode.
You can follow us on X, Facebook, and Instagram at Cosmic Savannah. That's Savannah spelled Savannah. You can also find us on YouTube, where audio-only episodes are uploaded with closed captions, which can be auto-translated into many different languages, including Afrikaans, isiXhosa, and isiZulu. I don't know about Setswana. We should work on that.
Special thanks today to Professor James Chibueze for speaking with us. Thanks to our podcast manager, Francois Camphor, our social media manager, Sumari Hatting, and our audio editor, Jacob Fine.
Also to Mark Allnut for music production, Michal Werchek and Brian Masamula for photography, Kyle Jones for astrophotography, Susie Karras for graphic design. Thanks to Emil Menkis for video creation and Moses Makungo and Abigail Tamaran for transcription.
We gratefully acknowledge support from the South African National Research Foundation, the Square Kilometre Array Observatory, the South African Agency for Science and Technology Advancement, the South African Astronomical Observatory, and the University of Cape Town's Astronomy Department.
You can subscribe on Apple Podcasts, Spotify, or wherever you get your podcasts, and we'd really appreciate it if you could rate and review us and recommend us to a friend.
Re tla bua le lona gape mo episode e latelang ya Cosmic Savannah.
Yeah.
Cool. Could you give us an example of maybe like the tent analogy in Setswana?
No, you put me on the spot.
No, it's a lot of pressure.
Yeah.
We won't do that to you.
Thank you. Thank you, Dan, because Jacinta did that to me.
I won't do that to you.
Thank you.
Oh, Dan.